Dear friends, hoping that you are fine and working hard to excel to score best grades in the external exams. Coming external exams in May June 2025. For right now, we are solving the paper under our consideration is October November 2024, paper 4 variant 2, and we will be solving in this video question on nuclear and atomic physics as well as space physics, the last two blocks. So question number 10 is under our consideration. So carbon 14 6C14 is a radioactive isotope of carbon. Carbon 6C12 is not radioactive. Explain how an atom of carbon 14 differs from an atom of carbon 12. So two points we can give. One thing is very clear. See, carbon 14 is radioactive, so it means it is unstable as compared to carbon 12. Secondly, another thing you can say that see carbon 14. So what are the number of neutrons in carbon 14? 14 minus 6, there are 8 neutrons. Whereas in carbon 12, there are 12 minus 6, 6 neutrons. So carbon 14 has 2 more neutrons, as well as it is less stable as compared to carbon 12. So I can say carbon 14 has 2 more neutrons than carbon 12, and also we can say carbon 14 is not stable, or it is less stable than carbon 12. Next question is interesting. All living organisms contain both carbon 12 and carbon 14 atoms. The ratio of carbon 14 to carbon 12 is this 1:1 times 10 raised to power 12. Half-life of carbon is 5700 years. So when an organism dies, no new carbon is absorbed. The amount of carbon 12 in the dead organisms remains fixed, but carbon 14, as it is unstable, so it is decaying with time. So describe how the amount of carbon 14 in the dead organisms decrease with time. So two ways we can answer it, my dear friend. The remaining carbon 14, the remaining carbon 14 is decreased by half in how much time? In one half-life, which is 5700 years. This will give you 1 mark. And another point which you can say, that the amount of carbon amount of carbon 14 decreases at a decreasing rate. With time. Now this last line is a bit confusing. What does it mean? I will explain you. Let's suppose in the beginning, in the start, just as an assumption, I can say, let's suppose there were 100 grams of carbon 14 in a living body, in a living organism. when it is alive. So when 5700 years will be passed, the remaining amount will be exactly half of the initial value, which was 100 gram. Now remaining mass will be 50 grams. So how much is decayed, how much is decreased in 5700 years? That is 50 gram. Now the remaining amount is 50 gram. In another 5700 years, which is one half life of carbon 14, the remaining amount will be 25 gram. So how much is decreased? Of course 25 gram is decreased. Now see, in the first half life, mean 1 by 2 is remaining. After second half life, 1 by 4 is remaining. See, in first 5700 years, 50 gram is decayed, and in after second half life, how much is decayed? 25 gram is decayed. 50 gram is 1 by 2 of the initial value, and 25 gram is 1 by 4 of the initial value. So in the first half life, 50 gram decrease. In the second half life, 25 grams is decreased. So it means the decreasing magnitude or amount of carbon 14 is decreasing at a decreasing rate with time. So very important. And the same point, see, after first half life, 1 by 2 of the initial value is remaining. After second half life, or after 2 half lives, 1 by 4 will be remaining. After 3 half lives, 1 by 8 will be remaining, and so on. I'm sure it will be clear. So a sample of wood contains carbon 14 to carbon 12 atoms in the ratio, now 1:4 times 10 raised to power 12. Calculate how many years ago the tree died. So for this purpose, we need to know how many half-lives are gone. Half-lives, number of half-lives we can calculate by dividing the total time over the time of one half-life, by dividing the count rate, given count rate, by the ratio of the count rates. Now here we will be getting the number of half-lives by the ratio of this carbon 14 to carbon 12. For right now, when it is dead, so after some time, see how much is there? 1:4 times 10 raised to power 12 divided by, initially what was the ratio? It was this one. It was 1:1 times 10 raised to power 12. So now my dear friends, 10 raised to power 12 is cancelled with 10 raised to power 12. What is left behind? 1/4 over 1/1. This means 1 by 4. Now how many half-lives are gone? 2 half-lives are gone. As I told you, 100 gram was in the beginning. After one half-life, 50 gram is left. After one half-life, half of the original value. Another half-life is gone. How much is left? 25, because 50 divided by 2, 25 gram is left. So what is 25? It is 1 by 4 of original. 1 by 4 of 100, that is equal to 25. So how many half-lives? 2. So it means this implies that the number of half-lives is equal to 2. So then how many years ago? This is so simple. So it means the time, since it is dead, that will be 2 times 5700 years. 0, 0, 2 sevens are 14, 2 fives are 10, plus 1, 11 years. 11,400 years. If you want to write it as it is, or even you can write by rounding it off to the nearest thousand. So 11,100 years. Very simple. Now, another way to calculate it, we have one equation to calculate the half-life or remaining amount. Like I'm writing remaining atoms, it is equal to 1/2 raised to power n times original value or initial value. Original value. So 1/2 raised to power n. Here, what do we have? We have 1/4. So we can convert it in powers of 2. So we can write it 1 over 2 raised to power 2. So if I'm comparing now to get the number of half-lives, n is the number of half-lives. Here, what is n in this equation? Number of half-lives. If I'm just comparing this with this, 1 over 2, 1 over 2, n2. So this implies that number of half-lives n is equal to 2. N represents what? The number of half-lives. So if we have number of half-lives equal to 2, it means easily we can multiply one half-life with 2 to get the total time from since the tree was dead. Now, my dear friends, other radioactive isotopes have different half-lives. Suggest a use of radioactive isotope with half-life of 1 hour and explain why a short half-life is suitable for this purpose. So it is first of all, we can use this sort of isotope which is with the half-life, very short half-life of 1 hour, a short half-life. It is used in medical tracers, medical imaging, medical diagnosis, all of them almost same. So you can write medical imaging to diagnose the diseases, and it is not staying in the body too long. It is not staying in the body too long, as it has short half-life. No need to give this much detail, but medical imaging, it's not staying in the body too long, or you can say it is having low dose, or it does not damage the body, internal parts of the body, like this you can say. Now the next question, my dear friends, state the name of the one of the planet that has an orbit further away from the sun than Venus. Further away from the sun than Venus. So it is, my dear friends, further any, like Venus, it can be Earth, Mars, Jupiter, anyone further away from the sun. So we will write Earth. Then state the name of one of the planets that has the orbit closer to the sun than Venus. Only one option is with us now, and that is Mercury. Then Venus has an average radius of this is the radius of orbit, and an orbital period of 220 Earth days, so that is T. Calculate an average orbital speed of Venus. Give your answer in meters per second. Give your answer in meters per second. So V is equal to 2 pi r over T. So 2 pi times r is 1.1 times 10 raised to power 11. This is in meters, and we need the answer in meters per second. So okay, over period, that is 220 Earth days. So 220, each Earth day is 24 hours. Each hour has 60 minutes, and each minute has 60 seconds. So simplify, you will get the answer. And roughly, when we are calculating, answer is 3.6 times 10 raised to power 4 meters per second. Okay, next is then state the relationship between the orbital speeds of planets and their distances from the sun. We know if the planet is further away from the sun, The gravitational pull of the sun on the planet is weaker and its orbital speed is slower. So state the relationship between the orbital speed of the planet and their distances from the sun. So we can write the orbital speeds of planets decrease as the distance of the planets increase from the sun. So write like this: the orbital speeds of planets decrease as the distance of the planets increase from the sun. Next is now comet are balls of ice and dust. Some comets orbit the sun. Explain how the speeds of a comet changes as it orbits the sun, and explain your answer using the ideas about the conservation of energy. You may include the diagram into your answer. So you may include, it means even if we are not drawing, so it will not cause any difference. So we can say in terms of energy. Okay, my dear friends, so we can say as the comet approaches the sun, gravitational potential energy decreases and kinetic energy EK increases. It means comets orbital speed increases as it moves closer to the sun, but total energy remains constant. Total energy remains what? Constant. We have to say this point also, for the conservation of energy is there. So if we just think opposite to it, as the comet moves away from the sun, potential energy increases and kinetic energy decreases. So the comet slows down as it moves away from the sun, but the total energy, it will stay constant and throughout the orbit. Okay, my dear friends, I'm sure this is clear to you people. If there will be any question, doubt, or any particular question, paper 2, 4, 6, fresh years or old years, please you can write in the comment box on my channel, and inshallah I will be trying my best to respond as soon as possible. And if these recordings are useful for you, so please share this link with your family and friends and subscribe my channel. Take care. Bye.